Welcome to the notes for section 3.3. This mirrors pretty closely the notes from 3.2, which you should have already looked at this point, even though they're in the same section, because this is a similar conversation to what we had about addition and subtraction in multiplication and division of whole numbers. All right, so first, remember that kids start thinking about multiplication really in right around third grade. It's really the crux of third grade math ultimately. And then division is the end of third grade into fourth grade in many cases. But the idea in standards is very much that kids have to understand lots of different ways to represent multiplication and division so that they really get what it's about, that it's more than just times tables. Kids have to use properties of addition and multiplication to multiply numbers, to use more sophisticated strategies, to apply those things to solving problems. And we have to also think about how this is an algebra readiness skill. The idea that multiplication and division are is an inverse relationship, much like addition and subtraction are, is about eventually using those skills to do things in algebra. This is preparing them for later math. Yes, you're always going to need to multiply and divide, but you're also going to use that skill set to do other things. All right, moving slides. So there are a couple of models for multiplications of whole numbers in here. The first is repeated addition. Oh, I need a pen. Sorry. The second are arrays and areas. And the third is Cartesian products. So we're going to go through them one by one. First, repeated addition is exactly what it sounds like. We have 4 groups of 3 things. We can use addition to add 3, 4 times, right? So if I have 3 or 4 groups of 3 brushes, 4 groups, oh, still not using the right pen, pardon me. 4 groups of 3 brushes. Okay, this is 1 group of brushes, 2 groups of brushes, 3 groups of brushes, 4 groups of brushes. Okay, 4 sets of 3 objects. It's like I talk with my kids. They'll have my daughter right now is doing a lot with money, so she had 3. If she had 4 piles of 3 pennies, how many pennies would she had? She likes the idea that there's a faster way to add. And that's really why we talk about repeated addition with kids, because eventually they get tired of it and they're like, oh, well, couldn't I just do this faster if I knew 4 3s was 12? It's like, oh, there it is. So we can also show repeated addition with blocks or on a number line where we think about it. Here's 4, here's 4, here's 4, here's 4, here's 4. So 5 4s is 20. Okay, but it's important that they think of it this way, that they use this representation. They see it a bunch of different ways because different ways click for different kids, right? The second way we want to talk about multiplication is with area and array models. So this is an array over here on the left. An array is usually like a series of dots or squares. This is 4 and 5, 5 across, 4 down. Now, you someday will be in a classroom, maybe you already have, where some teacher says, oh, the length always has to be the first number and the height always has to be the second number in your multiplication problem. That is nonsense, honestly. There is no rule like that, nor should there be, because what kids have to remember is if I rotate this rectangle 90 degrees, it then becomes 5 times 4 or whatever. So there doesn't need to be any rule about which label goes where when you build an area model or an array. It just, as long as they have 4 times 5 represented, it's fine. The model is to help them understand what the answer is, and if that's how their model works, then great. So area models are really important. Area models help kids learn to multiply. This is 5 groups of 4 or 4 groups of 5, depending on how you look at it. So it helps them get a picture in their head that they can then return to get a quick answer. But it also is then, area is a skill, right? We used area in geometry. We use area then to find volume. We use area in algebra, okay? This area model here in 3rd grade turns into a model that will help them multiply polynomials later. So it's this particular model for multiplication is, in my opinion at least, one of the most important because it sets up so much additional math down the line. If they get what an area model is, it really solves some things for them. So some formal definitions here. For any whole numbers, a and n, where n is not equal 0, n times a is n, the a, n times. So it's n quantity of a's. If n equals 0, then a times 0 is 0. This is the identity property, right? Anything times 0 is just none. If I multiply 3 toothbrushes times I don't have any of them, I don't have any of them, okay? A Cartesian product model really sounds much scarier than it actually is. So you're going to take 2 web-based courses at college. You're going to take one of the following, either world history or ancient history. And for your second course, you can take Latin, German, or French. They all sound like a hoot online, right? To show the number of different schedules you can make a tree diagram. So we could do, I have to take a history, I have to take a language, right? So I'm going to take world history or ancient history. And then for my language, I'm going to take Latin, French, or German. Or Latin, French, or German. Well, that means all the combinations are world history with Latin, world history with French, world history or German, ancient history or Latin, ancient history or French, ancient history or German. How many products do we have? Well, we have 1, 2, 3, 4, 5, 6 different kinds of opportunities, right? That means that my 2 choices times my 3 choices, 2 choices times 3 choices, got me 6 options, right? We know 2 times 3 is 6. This is just a different multiplication model. All right. Sorry. So we designed our schedule from those sets, and we made our tree diagram, right? We did that a minute ago. So world history, Latin, right? And we get all the choices. We end up with 2 times 3. We end up with 6. Okay. This is also the fundamental counting principle. It's a part of probability. We've seen it earlier, or if we didn't see it earlier, we'll see it again. But it basically says that if you have this many choices in group A and this many choices in group B, you multiply them together, that's how many choices total. A lot of times you'll see this in problems like Joe and Mary were going to an ice cream sundae bar. There were 3 flavors of ice cream. There were 4 kinds of sprinkles. There were 2 kinds of toppings. How many different sundaes can they make? Well, 4 times 3 times 2 gets me 24. We have 24 sundaes. That's the fundamental counting principle. It's also a Cartesian product model. Okay, so technically, for finite sets, set A, remember capital A, capital B, n of A, the number of things in A is little a. N of B, the number of things in B is little b. Then the n of A, the number of things in A, this A, times the number of things in B is the Cartesian product of the number of things in the Cartesian product of set A and set B. This is an overly complicated way to state this, right? But it's a definition. A times B here, it's the cross product, the Cartesian product. The numbers are multiplied, but the sets themselves are not. Like, why? There is no real thing to get if I multiply Latin by world history. Like, that's not something you multiply. There's no thing I get if I multiply chocolate ice cream by peanut butter, although delicious. So remember here, we're talking about the number of things in that cross product set, not the things themselves. All right, so some properties of multiplication, closure. Just like we did with addition, for certain sets, multiplication can be closed. So if I have A and B, their product is a unique whole number. A set is closed in multiplication if that result is in the set, just like it was for addition. Multiplication is commutative. So 4 times 5 is the same as 5 times 4, which is why we don't want to tell them which direction their area model goes, because it doesn't matter. Multiplication is also associative. So 3 times 4 times 2 is the same as 3 times 4 times 2. Doesn't matter which way you do it, just matters that you multiply them. This is an example of an area that's showing it as a commutative model or property. So 3 times 5 is 15, 5 times 3, still 15. This is the same model. Kids might see them differently. Sometimes kids always use this set of rows as the larger number. It doesn't matter. They would think about this as 5 rows of 3. And you could think about this as 3 rows of 5. Either way, still makes 15. What this turns into, though, is the associative property, right? So I could do layers. And this is where we transition from area to thinking about volume. When we're just doing commutative, we're in 2 dimensions. In associative, we're in 3 dimensions. So all of this stuff wraps into a larger understanding of math together. So if we think about this one, this is 5 times 4 on the bottom, 5 groups of 4. And then I have 3 layers of that, 5 times 4 times 3. Here in the second model, I have 3 groups of 5, 3 times 5, and I have 4 layers of it, okay? Here, I can look at this as 3 groups of 5 times 4, right? Or 4 groups of 5 times 3, same thing. All doesn't matter, but it helps kids to think about layers and volume. Okay. The identity property of multiplication is 1, because then 1 is the number that you multiply by something, you get that number back, right? And the 0 multiplication property says that when you multiply something by 0, you get a 0, no matter what, okay? These are things you've known a long, long time. This is just the formal statement of them. The last one right here is distributive. Technically, the distributive property of multiplication over addition and over subtraction are different, okay? Because there's an additional rule here in the subtraction. But basically the idea is if I have A, B, and C, and I have B and C in parentheses, I can distribute the A to both. Whether there's an addition sign in there or like there is down here on the bottom, a subtraction sign, doesn't matter. It carries with. And you guys have done enough algebra in your lives at this point to know that that's the case. You just take the sign that's there. So A times B plus A times C. A times B minus A times C. Sorry, too many words at once. So this is just a picture of the distributive property. This is 5. So here's my 3 plus 4 here. And this is 3 plus 4 together. And this is 5 rows of 3 plus 4, which is 7. But I can take them apart. I can cut it here, right down the middle. Take my scissors. So that means I have 5 times 3 plus 5 times 4. You can see in the picture that if I added this back together, I smushed them, I'd have the same thing. And a lot of times kids actually need to see this to believe the distributive property because they think it's sort of fishy. They don't always right away go like, oh, yeah, totally, that totally works like that. It's fine. We can also, commutative, since we have the commutative property, the A when you distribute can go at the back end of, so sorry, I don't mean that like that, of the parentheses. It doesn't matter where it is, it just matters that it's here somewhere if you're going to distribute. It doesn't have to be in front of the parentheses. Basically though, in our, you don't call people by their last name than their first name, right? In math, typical math language, we put that A first, so we know to expect it. That doesn't mean it can't go here. The other thing is that we can distribute to a number of things inside of parentheses. There can be 10 things in here. There could be 1,000. There could be 1,000,000. There could be 2. It's going to work either way. Distributive doesn't matter how many things are inside there. All right. We can also undo the distributive property, right? So if I have A plus AB plus AC, I can pull out that A, that's the common term, right? The greatest common factor, and write A times quantity B plus C. This is your favorite fun friend, factoring. You've done it before, you'll do it again. We do a tiny little bit of it here, but it's like if I had 2x squared plus x, I would factor out an x and get 2x plus 1. That's all it is, same difference. That's all that rule says. But when I do this x and the 2x plus 1 are now both factors, okay? All right, this is what eventually becomes of area models, okay, down the line. This is technically multiplying binomials, right? A lot of times this would be more like x plus 1 times 2x plus 3. Forgot my x. I don't have much of a voice today, so forgive me. I have a little cracky voice going on here. But what you see here in my area model is that this is z plus w across the top. I can put the plus sign in. And x plus y along the left. Then we just we multiply them, we distribute, right? If I did FOIL, I'd do x times z. X times z gets me xz. And then I would do outer, x times w. X times w gets me xw. Inner, y times z right here. Last, y times w gets me yw. That's how it works. That's why we do it. This is the physical representation of that process. And it's important for kids to see, because someday when they have to multiply this binomial, if they need a picture, they can draw one. One of the other games you're going to play in here is multiplication top it, but you know from the last video that you are going to read the rules, find a partner, and then it's part of your written assignment for this section. This is just like addition top it, except you're multiplying instead of adding. All right, so that's the multiplication models. See, it wasn't terrible. Now we got to talk about division models, and these really are among the most important models, because really, if you think about learning operations with kids, division is really the operation that kids fight. You know, addition is fine, subtraction isn't always the most fun, but kids get there. Multiplication is okay, and then division, people still you're probably cringing now just hearing about it. So when we talk about division, we talk about 3 models here: set partition, missing factors, and repeated subtraction. So when we think of set partition, it really is exactly what it sounds like, and it is the most common sort of little kid version of a problem. It's something you do all the time. We have 18 cookies, and we want to give an equal number of cookies to 3 friends. So how many does each person get? And what you would literally do with kids to start this is you would give them bingo chips or cookies if you're feeling crazy, or some sort of representation of 18, and ask them to pass them out to 3 friends and see how many they get. We can divide 18 into 3 groups, and each friend gets 6. Division. This is partitioning a set. I had 18 in my set, and I divided it into 3 equal groups. Okay? All right. The missing factor model basically is the reverse thinking here. If each friend in my story got a certain number of cookies, C cookies, then 3 friends receive 3 times C cookies. If 3 times C is 18, C has got to be something. 3 times what gets you 18? Well, they would know 3 times 6 is 18, because your kids will know their multiplication facts by now. So this is sort of a strange way to do this. And you may not have been shown this way in elementary school, or maybe you did and you tried to block it out. But this is actually really important because you're not asking them to solve an equation here necessarily. You're just asking them to write it and then to think about what number has to go in here for C. But eventually they see like, oh, well, 18 divided by 3 would get me 6, wouldn't it? And they'll start thinking that way, whether or not they're actually going through the process of showing that this is a division. You start them on the path to solving equations using inverse operations in 3rd grade. Look at them go. So in division of whole numbers, for any whole numbers A and B, where B is not equal 0, because we cannot divide by 0, that's undefined, right? A divided by B is C, some number C, if C is a unique whole number, such that B times C is A. All that says, basically, is if I did 10 divided by 2, I have to get some number such that 2 times whatever that number is gets me back to 10. They're just a fact family, right? So this number has to be 5 because 2 times 5 is 10. That's all that definition says. Repeated subtraction is a really common thing for kids to do. Heck, I even do it every now and then because it's a little easier than doing a crazy division. So imagine you have 18 cookies and you want to package them in boxes and they hold 6 cookies each. Well, I saw my daughter do this the other day because she was trying to make groups of something for her stuffed animals that she makes all sorts of crafts for. So she has 18 cookies and she wants to put them in the boxes. So she takes 6 away, that's 1 box, and she's got 12 left. Then she fills another box, takes 6 away, has 6 left, that's 2 boxes. The last 6 cookies fill another box, so that's 3 boxes. 3 boxes of 6 cookies is 18 cookies. And you see that as I say stuff like that, I write out the equations. It's really important that you get kids to represent their math, the words that they're saying, in symbols. You can also say, oh, remember that we divided 18 cookies into 3 boxes. Or let's do that different. We divided 18 cookies into groups of 6, and that gave us 3 boxes. Okay? But if you put the equation, you always put the equation to the words you're saying, they will do that for themselves eventually. It takes time, but the more practice everybody gets, the better you are at anything, right? All right, so the division algorithm technically says that given any whole numbers, A and B can't be 0, there exists some number, Q, and a remainder such that A equals B times that number plus whatever's left. Because if you think about it, say I want to divide 15 by 2. Not everything is going to come out equally, right? I might have 15 cookies and I want to give every friend 2, and I'll have 1 left over to give my mom because she likes cookies. So 15 divided by 2 is going to be 7 with 1 left over, right? 7 times 2. Okay, so here's our division problem. Basically what that says is 15 is equal to 2 times 7, right? Here's our product, and that was our quotient, Q, plus the remainder, 1. Do you see how that lines up? Let's do it again real quick. So I had 15 divided by 2, and that got me 7. Okay, remember that in division, the number that you result in is called your quotient, remainder 1. What that means is the definition of this division is that 15 is equal to 2, which is what I divided by my divisor, times the quotient, plus the remainder. Okay? When A is divided by B and the remainder is 0, we don't care about this remainder. And technically, we can say that A is divisible by B. So if I had 14 instead of 15, all I would get was 7, right? Because 14 is even. 14 is divisible by 2. All All right, so here's the one scary problem in this section. If 123 is divided by a number and the remainder is 13, what are the divisors? What could I be dividing by? So take a second, pause the video, go see if you can figure it out. Remember that I know that 123 is going to be something times a quotient plus whatever the remainder is, right? See if that helps. Okay, hopefully you paused and looked at this. So what's the first thing I have to do here? I know the remainder is 13. So the 13 actually doesn't matter for my quotient, does it? I'm going to take it off. So 123 minus 13, because that 13 is going to sit over here on the side, is 110. All right, well, now I need to think about what I could do to make this BQ, right? What are the different ways I can calculate, multiply to get 110? Well, I could do 1 times 110, right? I could do 2 times 55. I could do 5 times 22. I could do 10 times 11. Okay. So these are all the different products I could have. Do all of them work? Could they be a possible divisor? And the reason, so if I did, for example, 123 divided by 2, would I get the solution to the problem and have the remainder be 13? Well, no, right? Because 123 is odd, but 122 is even, so I'd get 50. 100 divided by 2 is 50. 22 divided by 2 is 11. So I'd get 61, remainder 1. Well, that doesn't help, so I can't use a 2. What happens if I use a 5? Well, something not totally dissimilar, right? 100 divided by 5 is 20. 20 divided by 5 is 4. So 24, I get remainder 3. That's a bummer. Would 10 work? Well, you decide. What do you notice here? I will tell you that I know that 22 works, right? 123 divided by 22 gets me, let's see, 22 times 5 is 20 times 5 is 100. 10 times 2 times 5 is 10, so 110. 110, remainder 13, that works. What do you notice here? Do you see it? So for me to get a remainder of 13, the number I divide by has to be bigger than 13, right? Because if it's not, what's left over is smaller than what I need as my remainder. So for this problem, the divisors that will work is 110, 55, and 22. If you don't believe me, go through and divide by each of them and see how it works out. All right, so remember, you can use this picture to relate multiplication and division, as well as addition and subtraction. So multiplication and division are inverse operations. Addition and subtraction are inverse operations. Repeated addition gets you multiplication. Repeated subtraction gets you division. Okay, this is the relationship. I love this picture. So I've actually given this to lots of years of kids in school because it's a really nice way for them to remember how it all connects. All right, and so the end of this is dividing by 0 and 1. If n is any non-zero number, so say it's 5, 5 divided by 0 is undefined. Anything divided by 0 is undefined. 0 divided by 5 is just you didn't get any. It's just 0. Like if I have 5 slices of pizza and I didn't give you any of them, you got no pizza. And then 0 divided by 0 is still undefined because dividing by 0 is always undefined. So you do not divide nothing by nothing and get 1. That's not right. 0 divided by 0 is undefined. Okay. So, oh, look, there's more. I lied. Oh, that's right. I forgot this was at the end. So remember, this is the beginning of, now that we have 4 operations, we have to start talking about order of operations. This is the thing that maybe you'll hear more and more about this that drives me craziest in life, because I've been in classrooms over the years, plenty of them, where somebody teaches order of operations wrong. Somebody, I bet you about $100, taught you order of operations wrong. When no parentheses are present, multiplications and divisions are always performed before additions and subtractions. They are performed in the order that they occur from left to right, and then additions and subtractions are performed in the order they occur from left to right. That means that if what you have is a series of multiplication and divisions, and the divisions come first on the left, you do that first. Multiplication does not come before division. So order of operations is always parentheses, exponents, multiplication and division from left to right, whichever comes first, addition and subtraction from left to right. So do this one down here on the bottom. See what you get. All right, you paused, you did. What did you do first? You did 9 divided by 3, right? 9 divided by 3 is 3. And then I like to rewrite because it helps me see things. What are you going to do next? You're going to multiply. So 3 times 2 is 6. And now what are you going to do? Subtraction, addition and subtraction from left to right. So 8 minus 6 is 2. 2 plus 3 is 5. So if you didn't get 5, make sure you follow along, because this will not be the last time we see order of operations. There will be more. All right, so from here, you will need to go do the MyMathLab work for 3.2 and 3.3. You will do the written assignment, which is games this week, and then participate in the discussion as well as the worksheet. If you have questions, you know how to get me. Please reach out and ask. Good luck, and we'll see you next week for the next video.